I'm on, right, excellent. So I won't waste any time at all. So this is a part of the talk I gave at ScalaSphere a few days ago, and I thought it might be of interest to all of you as well, so I put my name down. So the first part of the talk which you won't see was all about sort of micro-optimization within inside the Scala compiler. So I spent a lot of time recently working on changes to make, let me just start the timer, just so I keep track of myself, make changes to how fast ScalaC works, which I'm sure you all care about a lot. So I've done a lot of micro-optimizations and I'm involved in the big effort, which is one of the reasons Scala 2.12.5 is so much faster than Scala 2.11.9. But the problem is, most of the changes I find, if you open the Scala compiler, I will promise you can find things that you might want to fiddle with, because you'll look at the code and you go, oh, that's a bit, especially from a performance perspective. But then you get to the point, so I make a micro change, and I know the Scala compiler does a lot of work. It takes, 10 seconds, let's say, for a small project to do something to compile your project with a few thousand lines of code. In fact, the example I'm using is akka actor, so about 36,000 lines of Scala. And on my laptop, it takes about 6 seconds to compile on 2.12.5. So the interesting thing is the compile times change. So this graph is showing the compile times. I've run the same compilation in the same JVM 500 times, basically in a tight loop, just to see two things, how it changes over time, and also how it compares. So there's actually 6 tracks on this graph. 3 of them are the run of the original compiler before the change, and 3 of them are the run of the compiler after the change. So there's 2 things I want to point out on this graph before we dive into further details. Number one is I clearly haven't made a huge change. Right? If I'd made a huge change to performance, it would be immediately obvious on this graph, but I'm not expecting to. The change, the kind of level of change I'm expecting to make in the change that was on the previous slide is 0.2%. It's tiny, but those all add up over time, right? We make a lot of those, things get faster. So the first thing is, the very first compile, when you open up SBT and compile things, it actually took 22 seconds. Right? The first time you compile something with a clean SBT, it'll take 4 or 5 times longer than it will when it's warmed up. So if you ever see that message on SBT that says, please run it in interactive mode and don't keep restarting SBT from the console, that's why they added the message. So very quickly, after about a minute's worth of computation, the build times have come down and stabilized reasonably well. So that's about how long it takes to warm your compiler up, to get it up to speed, to work as fast as it can. So that's the JIT kicking in. But the other interesting part on this graph, so we've got the JIT warm up, is the fact that at some point, JIT went wrong. So if you look at this bottom end of the track, there are 2 of these paths that after 400 or so compilations decided, well, we can do better. Let's optimize it a bit further, and made it 50% worse. So warm up your JVM, but be aware that at some point the JVM can actually get it wrong. It's over-optimization. So, so I'm going to drill in. So I'm going to drill into this middle section. I'm going to knock off the top and bottom so we can try and work out whether or not my change made any difference at all. Now, what I'm going to do is I'm going to color the new code in red and the baseline in blue. So does anybody want to make a bet whether I've made it faster or not? So these are all the different runs, about 300 runs. Yeah. It's actually really hard to tell. It's really, the JVM's performance is really noisy because you've got GC, you've got other things going on. So what it turns out is actually it's really hard to even work out whether you've made a small difference. So we're going to step back one step further. I'm just going to look at the baselines. So I'm going to remove the 3 new changes, and I'm going to focus in on the baseline changes just to see if we can work out a way of getting good numbers. So here's the 3 baselines. And the interesting part is, what I've done is I've put the sort of average lines on these 3. Actually, the green one's a bit hard to see, But if you look at the red one and the blue one, so this is exactly the same code. So I haven't recompiled it. I've just closed down the JVM and started it working again. Right? But one of the weird things is the difference between the red line and the blue line is about 2% of the entire compilation speed. So restarting my JVM, if I'm lucky, the JVM will run faster. So when I first started making changes, I would run a change and it'd be like, it's faster. And then run it again and the change is gone. And then run the baseline was faster. And I was horribly confused by this, as you can imagine. But the other weird thing is the green line, which is actually really hard to see on this slide, actually starts below the blue line and ends up above the red line. So can I get I can't really do my cursor from here. But it's actually really hard to tell whether you're making micro differences. So one of the things we have done, the people I'm involved with, is we made a tester to actually try and run this stuff a bit like JMH, but JMH is great when you're trying to test a micro benchmark, a tiny little snippet of code. When you're trying to do it in the large, it doesn't work well. And JMH has some limiting problems. Go and read up on the docs if you're interested. So when you deal with, if I benchmark a tiny bit of code, the JIT is very good at going, oh, there's no other implementation of this code. I can optimize it really, really hard. And the classic example of that is any method. So if you do size or length on a list, it will go, oh, there's only one length implementation loaded into the JVM. So I can effectively turn that into monomorphic dispatch. I can fast path that code. And the moment you load vector, an array, and other classes, it goes, oh, wait, no, there's more. Yeah, okay, I'm going to stop in 1 second. So one point I'd like to add is these are the best numbers I've ever produced, and there's a whole bunch of stuff to do it. And whilst you can't tell on the CPU, we actually reduced the memory footprint by about 40 megs on a compilation of this project. So there you go, a very quick one, but get involved in compilations. It's lots of fun, and you'll learn things. Thank you very much. Lightning talk, I love it.